So now. Okay. Good afternoon, participants. So from today we are starting this our module 1 part. Okay. This part will be taken care by our lecturer, Professor Sunil K. Ghosh. Okay. So only thing is this from today onward, our actual NMR course will be starting. So we try to follow the course as far as possible. And in between, if you have any doubt, directly you can ask to our lecturer. He will be happy to answer your questions. You can send questions to his email ID also. It is already shared with you all. And you can also write in the chat box. And after his lecture, actually, you will be unmuted, so you can ask also. Okay. So with this, let us start this course. And I request Dr. Sunil Ghosh to start with. And one more thing, all the participants, please register your attendance in the chat box with your registration ID. Okay. Okay. All the best, Professor Ghosh. See you next time. You sit here, maybe. Directly. So good afternoon, participants. I welcome you all to this advanced NMR spectroscopy course. So today onwards, we'll start the part 1. So in part 1, I'll be taking 12 classes in module 1. Okay. So in module 1, again, today I'll be talking, I've divided into 4 sections. So I'll start today section 1. Okay. Now, if you want to read some books from which I am teaching, I am mostly following 3 books. One is Understanding NMR Spectroscopy by James Keeler. Then the other one is Modern NMR Spectroscopy by R.S. Macomber. And third one is NMR Spectroscopy by H. Gunther. Now, in the introductory course, Professor Arindam Ghosh has taught you the physics of spin systems. Okay, so I'll be not be going into the detail of those spin system, but definitely I'll use those informations. So those who cannot follow these things or would like to understand the things in detail, I request them to go through the video or the presentation of Professor Arindam Ghosh. If you have any difficulty, or if you have doubt, you can send email or ask me during the lecture or after the lecture. So now let us see the spectroscopy. So why do we study spectroscopy, or what information we get from spectroscopy? So if you see, the spectroscopy deals with the interaction of electromagnetic radiations with a molecule, because we are chemistry people, so we'll call these molecules, or you can consider this in general terms as matter also, to give structural information. Now we know that light interacts with various intrinsic molecular motions. So intrinsic molecular motions are the motions which are present in the molecule, which does not require external influence for those motions. Like if you consider the bond rotations, you don't have to give any energy, so that the rotations are always taking place. Similarly, the bond vibrations also, and electronic motion. So these we call the intrinsic molecular motion, and the light interacts with this motion. So if you consider that in terms of quantum mechanics, these interactions are explained in terms of energy levels. So in energy levels means these energy levels, or there is a requirement that if the light is to be absorbed, there is an energy requirement for the photon. Okay, and that is decided by the energy
level, the difference of the energy level, energy of the two energy levels, the higher energy state and the lower energy state, that is the delta E is equal to E2 minus E1. E2 is the energy of the higher energy state and E1 the lower energy, and that should match with the photon energy, that is nothing but h nu. Nu is the frequency of the radiation. Another important quantum mechanics term is called selection rule. So selection rule actually tells about the probability of a photon to be absorbed or emitted. And we know that molecular motion that takes place due to absorption of a photon should conserve its angular momentum. You know that all these light, they have a angular momentum of 1, and that should be conserved during this process. Now let us see, that is the quantum mechanical picture I told you, because in NMR we will be using often quantum mechanical picture also, as well as classical mechanics. So we should know what do you mean by resonance in classical mechanics. So if you see that in classical mechanics, that if you see a particle, it is having an intrinsic uniform periodic motion. The periodic motions I told, like bond rotation, bond vibration, electronic motion, you can consider them as a intrinsic uniform periodic motion of the molecule, and so automatically they have a characteristic fixed frequency, and that should match with the frequency of the absorbed, or sometimes there is emission of proton, so the frequency should match with the photon. So this new motion, the frequency of the motion should be equal to the frequency of the photon. So what happens during resonance? So during resonance, these photons oscillating electric and magnetic fields, or electric or magnetic fields, they constructively interferes with the oscillations of the particles' electric or magnetic fields. So that is called the resonance. So if when the frequency matches, there is a constructive interference. Okay, so that is in classical mechanics we describe the resonance in this way. So only then absorption of the photon takes place. However, so these whatever I told you about, that these are the light directly interacts with the intrinsic motion of the molecules. But however, under certain circumstances, it is possible to engage particles in additional forms of periodic motion. So these are not present, but we can engage them. So what you have to do with the aid of an external force or field. Okay, so NMR spectroscopy belong to this. So what you will do, will bring that extra form of periodic motion with the aid of an external force or field, and in case of NMR, we will be using the very strong magnetic field. Okay, but still, if you want to achieve the resonance condition, okay, or resonance, you need to use a incident radiation with matching the frequency of this induced motion, that is masked. Okay. Now let us see NMR spectroscopy. So as the name suggests, the NMR spectroscopy is related to the magnetic properties of the nucleus. Now, NMR is specific to an isotope. You will see that an element can have many isotopes, but not all of them are NMR active. So only isotopes whose nuclear spin is greater than 0 are NMR active. Okay, so that is the condition. The spin of the nuclear spin of the NMR active isotope should be greater than 0. Now let us see what decides the spin of a nucleus. Okay, so parity of proton and neutron is important. Okay, so that decides the nuclear spin. So you can see that a proton spin can pair with another proton spin. Similarly, a neutron spin can pair with another neutron spin. But a proton spin cannot pair with a neutron spin. So when there is a mismatch, then only you will see there is a nuclear spin. And you can see that considering those situations, there could be 4 situations. Okay, depending on the number of protons and neutrons, we'll see there are 4 kinds of situations happening, which have been tabulated here. For example, if your proton number is even and the neutron number is even, so automatically the mass number will also be even, and in that case, the nuclear spin will be 0. So when this is all protons are pair, all neutrons are pair, so the nuclear spin value is 0. And the most popular example is the carbon 12. It's NMR inactive, or I is equal to 0. Similarly, 16 oxygen, 18 oxygen, 32 sulfur. But when proton is odd and neutron is even number, so the automatically mass number is odd, you will see half integral spin. Okay, like the examples I've shown, 1 is 15 nitrogen, 19 fluorine, 31 phosphorus. They have I is equal to half, but it can be more also, like 7 lithium, 11 boron, 35 chlorine, or sodium 23. They have I value 3/2. Even you can have a higher value, like for aluminium it is 5/2, and more than 5/2 is also possible. The third case is that you have done even number of proton and odd number of neutrons, so mass number is odd. Then also you get the half integral spin, like 29 silicon and 13 carbon. Carbon 13 both are spin having spin value of half, whereas sulfur 33 is having spin value of 3/2. Oxygen is 3/2. And the fourth situation is that when both are odd, so the mass number will be even. In that case, you will see the integral spin value. For example, the 14 nitrogen and deuterium, you will see the spin value is 1, whether if you can get a very higher integral number, for boron 10 is 3. So what we saw, that isotopes with spin I greater than 0 can have multiple spin states. Okay, when you immersed in an external magnetic field. So we have seen the part, the role of nucleus. Now, if what is the role of external magnetic field? Okay, so if you put a nucleus with which is having I greater than 0, it creates several nuclear spin states, and those spin states are labeled with the nuclear spin quantum number m. Okay, the total number of possible spin state, that is called the multiplicity of that state. Okay, those are with they will have different values of this spin quantum number m is determined solely by the nuclear spin value I. So for a spin value of I, the multiplicity is 2i plus 1. So that means it can make 2i plus 1 states. It's starting from minus I, then minus I plus 1 to ultimately to plus I. For example, for nuclei with spin half, the possible spin state will be plus up and minus up and plus up. Similarly, if your spin value is 1, you will have 3 states now. Mi values are minus 1, 0, and plus 1, or I is equal to 3/2. Spin states are minus 3/2, minus up, and plus 3/2. So when this I value of the nucleus is half, then the nuclei is spherical and it is called a dipolar nuclei. But when the I value is greater than half, the nuclei is ellipsoid and called a quadruple nuclei. And we will see that this quadruple nuclei has a tremendous effect on the NMR spectrum. So, so that's why when you will have in a molecule, when you have a spin atoms, or let us say atoms which are having this I value greater than half, you will see the NMR spectra is affected. We will see when we deal with the NMR spectrum. Now let us see the resonance condition of a proton under quantum mechanical model. Okay, so now we have seen that a proton in the when you apply a magnetic field, a proton can only exist in 2 spin states. Mi is equal to plus up and mi is equal to minus up. Okay. Now, spin magnetic moment of the proton in the z direction, because we will be considering the z direction because we are applying the magnetic field always in the z direction. So that magnetic moment is represented by mu z. It can have 2 values. Mu z is equal to gamma h cross mi. Mi is the spin state, or you can say it is a plasma. For proton, it is, or you can say the plus minus gamma HI, or for proton, it is I is equal to half. So it is plus minus gamma H cross by 2. Where this gamma is nothing but the gyromagnetic ratio. Gyromagnetic ratio is a property of a nucleus, and it is fixed for a particular nucleus. And we will see later on that this is the this actually is the magnetic moment coming from the nucleus, and that is due to its spin. And H cross is the Planck's constant that all of you know. Now, this spin magnetic moment in the z direction has been elaborately discussed by Professor Arindam Ghosh during his introductory lecture. So, if you want to know a little bit more, you please go through his lectures. So now this magnetic dipole for like a proton having Mi, a plus and plus half and minus half can only two possible orientation with respect to z direction. Either it will be parallel or it will be anti-parallel. That means that the magnetic moment vector is now quantized. It can have only two values, so we can say that the magnetic moment vector is quantized. And also we designate this spin state like plus half as alpha state. This will be always used. If we say alpha state of proton means it is plus half, and beta state means Mi is equal to minus half. Okay, so occasionally we will use this alpha and beta, or sometimes we will use plus half and minus half. So they mean same. Now let us see resonance conditions. Okay, under the quantum mechanical conditions. So what we have seen that that alpha and beta states of the nuclei, they have the same energy at the beginning. So if there is no magnetic field, they have the same energy. That means they are in the degenerate state. So once you put the external magnetic field, which is represented here as B0, it can destroy this degeneracy, and that is known as Zeeman effect. Okay, so when there is no field, you can see all the spin magnetic moment are oriented in all direction. Okay, but as soon as you put the magnetic field, this spin magnetic moment orient either in the plus z direction or in the minus z direction. Okay, and you can see so that they have different energy, and you can see that so before the application of magnetic field, and when you apply the magnetic field, now you see the two states have been created. Okay, now when you apply magnetic field, this spin magnetic moment interacts with the magnetic field, and the interaction energy is given by E is equal to minus mu z B0. This is a energy lowering interaction. It is not a repulsive interaction. Now we know that for a particular spin state, the interaction energy can be expressed is equal to minus Mi. Mi is the M value of that state, the gyromagnetic ratio, the Planck's constant, and the magnetic field. So for proton, this energy difference between the two Mi state, you can find out from this relation, and if you do that, you will find that delta E is the energy of the higher energy state minus the energy of the lower energy state, and that comes to gamma H cross B0. So this is your the energy difference between the two states, and if you see this gamma is again the gyromagnetic ratio, and it has unit of radians per Tesla per second. Similarly, the magnetic field has unit of Tesla, and this gyromagnetic ratio, it can be both positive or it can be negative. So we will see later on that there are many nucleus where the gyromagnetic ratio is positive, and in some cases it is negative. So when the gyromagnetic ratio is negative, you will see the MI values will interchange. The higher energy, let us say in case of gyromagnetic ratio is negative and spin value is half, you will see the alpha state is of higher energy, beta state is of lower energy. So there will be interchange of the states. But in case of proton, this gyromagnetic ratio is positive. So now, when a radiation energy which matches this energy difference, a transition happens from alpha level to beta level. Okay, and this condition is called in terms of this condition is called resonance in terms of quantum mechanics. And I have listed here several nucleus which are most commonly used in NMR spectroscopy. You can see the proton, deuterium, and so many other isotopes, and their spin values are also tabulated. And also you can see that all these isotopes have different natural abundance, except for fluorine, sodium, 31 phosphorus, and cobalt 19. They are 100% naturally abundant. But if you see other, they have a different, like proton is 99.985, whereas deuterium is 0.015. Similarly, it depends on which isotope we are dealing. Even for the same element, the different isotope can have different I value. Okay, so it is not necessary that the I value will be same for the element. For example, here you can see hydrogen, it is half, whereas deuterium it is 1. Similarly, 14 nitrogen it is 1, 15 nitrogen it is half. Okay. Now, and the gyromagnetic ratio of the nuclei are also presented here. And if you see that if you use a magnetic field of 9.4 Tesla, you will see the proton resonance frequency will be 400 megahertz. You can see the carbon resonance frequency will be 100.6 megahertz. So, and deuterium resonance frequency will be 61.4 megahertz. Okay, and if you see the list, the proton has the highest gyromagnetic ratio. So, proton is very sensitive to NMR. Now, let us see, because we will be using occasionally classical, both quantum. Let us see what do you mean by what you see in classical model of NMR. Okay. So now what we have seen that when a nuclei with I is equal to half, for example, proton is immersed in a static magnetic field of B0, which is directed along the z-axis, it adopts two spin orientations, minus half and plus half, with different energy. Okay, that we have seen. Okay. Now, quantum mechanics tells this that the spin magnetic moment is mu z. It can't align parallel to or anti-parallel with B0. That also has been explained by Professor Arindam Ghosh in his lecture, and you will see that they maintain an angle of 54.74 degree for m is equal to half and 125.26 degree for m is equal to minus half. Or you can consider, if you consider from the minus z axis, it is minus 54.74. So they cannot align with the z axis. Okay. So now because that they are not able to align, so there is a classical process arise that is called the precession. Okay. So now we'll see what is precession and what is Larmor frequency. Now, as we have seen that they cannot align along the z axis. So this due to non-parallel arrangement with the applied field B0, a torque is developed. What is the torque? So the magnetic moment mu z interacts with B0, and the cross product actually gives you the torque. So now we know that mu z is gamma h cross. So it is the cross product of gamma h cross and the B0 is produced. So this, due to this torque, okay, the angular momentum vector, which is shown here, this is the angular momentum vector and this is the angular momentum vector of the nucleus, therefore traces about this external magnetic field axis, okay, with an angular frequency known as the Larmor frequency. We will use this. So due to this force, Okay, the torque, the angular momentum vector precesses. Okay, it can precess in either direction depending on, I'll tell you in which direction it will precess. For gyromagnetic, if the gyromagnetic ratio is positive, you will see that this precession is clockwise. Okay, and if it is gyromagnetic ratio is negative, it will be anti-clockwise. And this motion is, this angular motion is known as precession. So the precessional frequency is called the Larmor frequency, and the motion is called Larmor precession. So what we saw is that the nuclei is precessing around the direction of B0 with Larmor precessional frequency, and we give this frequency as omega 0. Okay, so one can calculate or one can find out this omega 0, and this omega 0 is actually related to the applied magnetic field and the gyromagnetic ratio. So omega 0 is the gyromagnetic ratio into B0, and the unit is the radians per second, and if you convert it, you get the frequency in hertz if you divide it by 2 pi. But if you see in this equation, there is no involvement of mi or the spin state. So the omega 0 is independent of the mi values. So all spin orientations of a given nucleus, whether it is a plus up for proton or minus up for proton, or let us say +1 for deuterium or 0 for deuterium or -1 for deuterium, all spin orientation of a given nucleus precesses at the same omega 0 in a fixed B0. Okay, so that solely depend on the term and B0. Now that is again the precession is shown here in this figure. So due to this precession, if you see the magnetic moment, precessional motions, if you see this magnetic moment vector tip, it is actually making a circular path. So this is the clockwise. So similarly, this is the clockwise path is for both for mi is equal to plus r as well as mi is equal to minus r. Okay, and as I told you earlier that you will see this clockwise motion when the gyromagnetic ratio is positive, and you will see a anti-clockwise motion when the gyromagnetic ratio is negative. I do not want to see, in many books you will see that when you see the clockwise motion, it is given a negative frequency. Okay, in many books it is given, and the anti-clockwise given positive frequency. But anyway, we are not bothered about the sign because it indicates only the sign of rotation, how the vector is rotating. Okay, so let us to remove that complexity of sign. We have considered that because most of the cases we will be dealing with proton, and the proton rotation is clockwise, and we'll consider this as a positive rotation. So let us see what do you mean by resonance condition in a classical mechanics for a single nuclei. So what we have seen that now we have used a magnetic field, and we have now created a motion. Okay, that motion is not an intrinsic motion; it is a created by due to the applied magnetic field, and that I told you during my in my third transparency that under certain circumstances it is possible to engage particles in additional forms. This non-intrinsic or periodic motion. So we have created a periodic motion using the magnetic field B0. Okay, but still, if you want to achieve the resonance, you need to use a matching radio frequency. Okay, or matching frequency of radiation that will match with the motion of the particle. Okay, then only you will get the resonance. Okay, so this is shown in this figure. If you see that due to the applied magnetic field B0, the magnetic moment vector is precessing with its precessional frequency omega 0. Now, if you want to bring it into the resonance, you have to apply a radio frequency field, which is with a field is radio frequency field, which I have shown is here as a B1 field, and with an angular velocity equal in sign and magnitude of this mu. This mu is precessing, so the the precessional frequency of B1 should be the same. Also, the sign of rotation, the sense of rotation has to be also same. And then you will see that the new, which is precessing, or the low energy state will now move from low energy state will now move from this low energy state to a high energy state, and automatically it will move from the alpha state to the beta state. And in classical mechanics, for a single nuclei, this we call as a resonance. Okay. Any doubt till now? Okay. So now we'll go to the. Now let us see when we record NMR, it is not a one nuclei. So I have shown you the resonance conditions in classical mechanics for one nuclei. But when you see really a sample, it is not only one nuclei. Actually, it contains a large number of nuclei, and you see NMR samples are in millimolar concentration. So the number of nuclei will be like 10 to the power 20 or more. And also we have shown that the two nuclear spin energy states, for example, for proton, we have created due to the application of the magnetic field B0, and those states are the alpha state, or EM, which is energy is equal to minus gamma H cross B0 by 2, and the beta state whose energy is gamma H cross B0 by. So again, I have shown that thing in this schematic diagram. Okay, so now when a radio frequency of matching frequency is absorbed, okay, so if you now we are applying a radio frequency, and if the frequency matches with that, and you will see that it will be absorbed, and nucleus goes from the low energy state, alpha state, to high energy state. Okay, so that is true for one nuclei, and we showed the resonance condition is delta I is equal to gamma H cross B0 and equal to the frequency energy of the electromagnetic radiation. But if you see in quantum mechanics tells that if you want to see this kind of net absorption of radiation, there has to be the two states should have different population, or the lower energy states should have more population than the higher energy state, or the N alpha should be greater than N beta. In a situation when N alpha and N beta are equal, you will see a stimulated emission, because in that case you will see both their emission and absorptions are happening, and so there will be no net absorption of radiation. And this situation is called saturation, and we will see that we'll use this saturation sometime in our NMR experiments. Now let us see what is this, how this relative population is decided. So this relative population, this N beta by N alpha, the population at the beta state by population in the alpha state at a particular temperature, is governed by another quantum mechanics law called Boltzmann distribution law. And all of you know this, what is Boltzmann distribution law? It is N beta by N alpha is equal to exponential minus delta E by KT, and N beta and by N alpha is always less than 1 and more than 0. And delta E, as we have already shown you, there is delta E is the energy difference between the higher energy beta state minus the energy lower energy alpha state, and that we have shown that it is gamma H cross P0, and that is equivalent to the energy of the photon. And K is the Boltzmann constant, and T is the temperature in Kelvin. Okay, so for proton, this N alpha minus N beta is very small. That means the population difference is very small, and you will see it comes in ppm. So if the population difference is very much small, then you will see that you will have a very poor sensitivity. So if you want to improve the sensitivity, so you have to either increase from this equation, if you see, you have to increase the energy difference, or you have to decrease the temperature. Again, the sensitivity, how to determine the sensitivity. So mostly in case of NMR, the sensitivity is determined by signal to noise ratio. And signal to noise ratio in case of NMR is given by, or signal to noise ratio is directly proportional to N, the gyromagnetic ratio of the exciting nuclei, gyromagnetic ratio of the detecting nuclei, the applied external magnetic field, and the acquisition time. Now you may say that when we are recording proton NMR, we will see the exciting nuclei and the detecting nuclei are same. But there are NMR experiments when you will see that we are exciting in one nuclei, but detecting in another nuclei. In those cases, you have to use the gyromagnetic ratio of both the nuclei. Okay, for simple proton NMR or carbon-13 NMR, it does not matter. Both gyromagnetic ratio will be same, but it will be different or depending on the experiment. We will see all those things when we use them. So how do we express the resonance in classical mechanics for a bulk sample? So before that, now what we have seen that there is a population difference, or we have to create a population difference, and that is happening due to the applied magnetic field. But let us see how much time it takes to reach these equilibrium populations, whether it is instantaneous or does it take some time. Okay, so if you put the sample in the magnetic field, how much time it requires to reach that equilibrium population, or between the alpha state and the beta state. As we have seen that when there is no magnetic, alpha and beta states are degenerate and n beta is equal to n alpha. But when B0 is on, the spin state establishes a new equilibrium as per Boltzmann distribution law with a slight excess of nuclei in the lower energy alpha state. That means finally the n alpha should be n beta. So the process of re-equilibration is not instantaneous. That means if you put the NMR sample in NMR machine and you cannot record the NMR. So how much time it should be kept? So it is governed by a quantity called the spin lattice or longitudinal relaxation time, T1. And these have been elaborately discussed by Professor Arindam Ghosh. You may see his lectures. So it is decided governed by the equation which I have shown here. N equilibrium minus nt divided by n equilibrium minus n0 is equal to exponential minus t by t1, where this n equilibrium minus nt is the difference between the equilibrium population and the population after a time t for a particular state. If you consider for alpha state, can calculate that, or beta state. And this subscript 0, this n0 actually tells at the time is equal to t is equal to 0. And n equilibrium, automatically this equilibrium, see, this is a kind of first order exponential growth, okay, of the population. So if you want to get that in equilibrium, you have the time has to be infinity. And this small t is called the time, okay, needed to get that level of equilibration. Okay, so let us see one example. It will be very clear. Okay, I have given you one example here. Let us say we have taken a certain set of proton nuclei and the temperature is 25 degrees centigrade, and I have given you the T1 value. Okay, so there are two problems. So calculate the n beta by n alpha if you apply the magnetic field of 5.87 Tesla. Okay, this is your first question. So that you can calculate. If you have to use this equation, straightforward this equation, and if you put the values of different, this is your gyromagnetic ratio of proton that you can get from the table, and this is your value of H, and these are the respective units for them. This is the magnetic field I told, 5.87 Tesla, and then this 2 pi radian, that value is given here, and then divided by KT. This is the value. This is the value of K, and this is the temperature 298. Okay, and you see this N beta by N alpha is very close to 1, but still it is not 1. That means the population at the N alpha state is slightly higher, and if you see that the difference is like this. So the N alpha is 0.50001 and N beta is 0.49999. Okay. So now that's my second question was that how long after immersion in a B0? Okay, so now we are putting the sample into the magnetic field of 5.87 Tesla. Okay, how much time it will take to get the equilibrium population 90%, 95%. Okay, see, we know that if you want to make it 100%, okay, then it requires infinite time because equilibrium that is not possible. So how much if you want to make it 95%? Let us see from this data. So we have given you the value of T1 is 0.2 second. So this is, see, normally you will see that T1 varies from millisecond to seconds. So it will be from 10 to the power minus 2 seconds to 10 to the power 2 seconds. So I have taken this 0.2 second. Okay. So if you solve that, so if you see that at 95% of equilibrium, N equilibrium minus NT. Now NT is nothing but it is 0.95 N equilibrium. So if you do that, you get 0.05 N equilibrium. Okay, and the denominator, if you see at T is equal to 0, because N0 has to be is 0. So now if you do that, so this N equilibrium minus NT by N equilibrium minus N0, you get this, and that is equal to your exponential minus T by T1. And if you put all those values, it becomes 0.05 is equal to exponential T minus T by T1. And you will see that you have to keep for at least for 3 T1 time to get the desired equilibrium population. And in this particular case, as I have given you, the T1 is equal to 0.2 second. So you have to keep at least for 0.6 second before you start your recording your spectrum. Okay. Now, if suppose if your the T1 for let us say some nuclei, you will see it is 100 second. For that, you have to keep at least 300 seconds. 300 seconds means you have to keep the sample for 5 minutes inside the NMR magnet before you start recording your NMR. So here I have shown in, schematically how the things build up. So when the before there is no magnetic field, there is no the population is same in both the state. Now as you turn it on, you can see that the population in the alpha state increases, and after 3 T1 you reach around about 0.95 or 95% equilibrium magnetization. Now if you turn off at this stage, you will see again the population is decreasing, and finally it will reach to the both the states will have equal population when the time is infinity. So at T is equal to 0 also they have equal population, but at T is equal to 3 T1, you can see there is a slight excess of population in the alpha state than the beta state. So here I have shown x plus 6 and x plus 4, where x is a very large number. Let's say it may be a million or more. So for your easy understanding. Okay, and as I told you that this T1 value can vary from 10 to the power minus 2 to 10 to the power minus 2 in solutions, because we'll be mostly dealing with the samples in solution phase. So let us see what is the resonance condition for macroscopic sample of spin half. Okay, so if you want to now in case of one nuclei, we have seen that the spin is flipping, but when it is a macroscopic sample, how to know, detect the how to know the resonance condition? So resonance condition can be you can say the macroscopic sample is under resonance if you can detect the NMR signal. So how to detect the NMR signal? So now you see that B0, the external magnetic field is applied along the Z axis. Okay, so how to detect NMR signal? So automatically you cannot put a detector in the Z direction, because it will detect that very strong magnetic field you put in the Z direction. So automatically you have to keep the detector to be placed in the XY plane, because in the XY plane the magnetic field due to B0 will be 0. So automatically you can detect only the spin magnetic moment which are coming into the XY plane. Okay, so only those can be detected. Okay. Now we have seen that under the equilibrium condition there is a excess spin in the alpha state. That also we have seen. Okay. Now if you see that although we have excess spin in the alpha state, but we cannot detect the any magnetization in the XY plane, because all the spins in the alpha state as well as beta states are randomly oriented. So the effective magnetization in the XY plane are cancelled out, and there is no net magnetization in the XY plane. So so automatically you cannot detect the NMR signal just only by putting the sample in the magnetic field, because that magnetization is 0 in the XY plane. And this part is also nicely explained by Professor Arindam Ghosh. You can see his lectures, the physics part of this, he has been explained nicely. Okay, now let us see the resonance condition for a macroscopic sample with spin is equal to half. So automatically when you are putting the sample in a magnetic field of where the magnetic field is the B0 is applied in the Z direction, okay, you will see that there is a equilibrium population of spin distribution, and you will see a net magnetization due to this along the Z axis, the M. Okay, as soon as you turn on the magnetic field, you will see there is a buildup of this M magnetization, and the build-up is followed by the, as I told, it will be followed by it will be governed by the T1 relaxation. Okay. Now, so and we have seen that although there is a population difference between the two states, but there is no net magnetization in the XY plane, and you have put your detector for detecting the signal in the XY plane to avoid the detection of B0. So automatically you cannot detect any signal. So what you have to do that to detect signal, you have to now apply another magnetic field. Okay, that is called the BO1. That magnetic field will be generated from the radio frequency. Okay, so we'll be applying a radio frequency field, okay, whose magnetic field strength is BO1 and rotating at the same frequency of the precessional frequency. So when this thing happens, okay, so what you will see that all magnetic moments which are precessing in different directions will now become phase coherent. Phase coherence means they will bundle up. They will have the now same phase. Here all the phases are different. That's why they were cancelling. The XY component is cancelling, but now they become phase coherent. Okay, so they now so automatically due to this phase coherent, M also tilt from the Z axis. Okay, so now you will see due to this phase coherency, there is a XY component magnetization, and that magnetization is also precessed at the same frequency around the applied magnetic field. So, and that the detector will detect that frequency. Clear this part? Okay, again I'll repeat this. Okay, so we have seen that this is, where is it? Okay. So now you see that this part I have explained to you. So due to this phase coherence, as I told you, the M actually tilts from the Z axis. That's why you are getting the MXY component which you are detecting, your detector is detecting, and that is also precessing at the same frequency as the each individual magnetic moments were precessing. Now this, as the M is tip way, so automatically it forms a angle with the Z axis. Okay, And so once you start detecting the signal, and that is called the resonance conditions in terms of classical mechanics of NMR. So what I told at the beginning, that if we can detect the NMR signal, okay, we call this as a resonance condition. And now when we apply the magnetic followed by a rotating magnetic field generated from the radio frequency, which is matching with the precessional frequency of this, making this all these spins to become phase coherent and now tilted from the Z axis. Okay, that is called the resonance condition. Now this tilting actually depends on two factors. One thing is what is the strength of the B1 field and how long this B1 field is applied. Okay. So that so this is called the flip angle, and that is so you can find out from the trigonometry that what will be the magnetization along the XY plane if the flip angle is alpha, and that is nothing but m xy is equal to m sine alpha. So how much this magnetization is tilted from the Z axis actually gives you the what will be the strength of the or mxy component. Okay, so that I told you, so, and that depends on the B1 field and also the how long this B1 is applied. Okay, so now if you see that we have applied the field and we have got this resonance condition. Okay, so and that we have found that mxy is equal to m sine alpha. Okay? And this oscillating mxy field now which is happened, and that is also precessing with the same frequency, the omega 0, and it is generating the NMR signal. And if you will get a frequency, and if you do that processing of that, you will get a NMR signal at that particular frequency. Now the question comes that when you will get the maximum signal intensity. Okay. Now if you see this mathematical equation that your mxy will be maximum when sine alpha is equal to, or mxy will be equal to the Z component magnetization before the radio frequency will applied, that is the m, only when sine alpha is equal to 1, and for that case the alpha has to be 90 degree. Okay, so we'll see that that means if you put a B1 field which can rotate, B1 field of particular strength or for a particular time which can rotate the magnetization from Z axis to XY plane, okay, is called a 90 degree. Well, we will see that when we discuss the pulse NMR, and that will be called or we will call it as a 90 degree pulse. Now, once you are, let us say you are doing a pulse NMR, and then if you remove the B1 field, now then the XY component does not go back to instantly to the Z axis, because you have brought the magnetization to the XY plane or a component into the XY plane. So it does not go back immediately, even if there is no B1 field. So it takes time. So there are two processes. So these individual magnetic moments begins to lose their phase coherence. See, we have made this phase coherence. So they lose their phase coherence in their XY plane, a process called spin relaxation. That also have been discussed by Professor Ghosh. That is called the T2 relaxation. So it loses the magnetization in the MXY plane, and also the system goes back to the Z axis, the random arrangement around the Z axis, okay, and or it is by a process called T1 relaxation that I have already discussed in a couple of slides back, and that actually finally gives you the MJ. So again, so once you record a signal, if you want to record another, if you want to do another experiment, you have to give enough time so that this M should go back to the equilibrium Z position again. And as I told you that there are two time constants involved for this process. One is called T1 and another is T2. T1 I have already told you, and T2 is nothing but the loss of magnetization in the XY plane. Okay, so I'll stop here. We get it right? Yes. So I'll stop here, and if you have any doubts and queries, you can ask.
So we can unmute the participants. And
Okay, you all are unmuted. If you have any doubt, you can enter into the chat box, or you can even speak also. No doubt, sir. Vijay Kumar. So if you have any doubt later on, you can send it by email, or again tomorrow I have a class from 4 o'clock. Okay, so you can ask during that time. You can go through my lecture, and if you have any doubt, ask me tomorrow. Okay, and please, if you want to understand the physics plus physics part properly, then you must also go through the lectures of Professor Orindam Ghosh. ঠিক আছে, বললাম।
okay, participants, then if you are happy, then we can stop it here. If you don't have any question, or if you find that there are some doubt at the later on, you can directly write to Professor Ghosh. I think you have already your this Professor Ghosh email ID, so you can send email to him directly, and he will be happy to answer it either through email or in the next class. So it is up to you to communicate with the professor how you feel like, okay, and try to get your doubts clear as far as possible. Okay, thank you very much. This one, given your registration ID, no, in the chat box, because your participation will be recorded through your writing in registration ID in the chat box. Okay, so be sure about that.